suppose f is continuous on a closed interval from a to b. Okay. So and let n be a number that has a value that between f of a and f of b, kind of in between. Then there is a number between a and b, say the number is c, such that f of c equal that number, n. Okay, so let's write it. Suppose f is continuous on the closed interval, and the interval is from a to b. So a to b are the endpoints of the interval. And suppose n is a number, or actually it's any number between f of a and f of b. We have one condition, that f of a is not equal f of b. Yeah? Then there exists a number c and that number is a number between a and b, like so. Well, actually, yeah, well, let's assume that b is greater than a, such that f of c equals n. Let's demonstrate this theorem graphically. We are not going to prove the theorem, but we're going to use its property. So here's some x and y coordinate system, and there is a function, a meandering function, like so. Function doesn't know where it wants to be, and it's defined. Let's define it from x equal a right here to x equal b right there, such that f of a, which is this value, is not equal to f of b, which is this value. Okay. So in this case, f of b is greater than f of a, and so we pick up any number between f of a and f of b, right? So I'll just pick up this value right there. So I'll call this number is n, at random, as long as it's between f of a and f of b. And what the theorem says, that there exists a number c. C is a number between a and b, such that f of c equal n. In this case, we have three of those, if you think about it. The first c, call it c1, is this value, where f of c1 equals n. The second one, let's call it c2, is this one. The third one, call it c3, is here. So in this case, we have three values of x between a and b, such that, and we call it c1, c2, c3, such that f of c1 equal f of c2 equal f of c3 equals n. Okay?
Is n arbitrary?
N is arbitrary between the two.
Okay. So if you put it down, you would have had just one value instead of three.
I'm sorry? Yeah, you can have, if that was like, if this function wasn't meandering like that, if it was a parabola, we would have only one. If the function is 1-to-1, by the way, then we have only one value like that.
But as it stands now, you need to hit all of those. My thing was in between on the y-axis of A and B, where it intersects the graph, you would have 3 points or 1 point.
You can have two. Because this function, I can go and finish it right there.
Okay.
So I can have 2. I can have 5. But the theorem says that there exists at least one number. That's a point.
Horizontal line at n of x, and that would become continuous, and you would have a value where c equals n at every point. So,
A horizontal line.
Right?
Yeah, that's why we.
You can have more than one.
But then f of a will equal f of b, and we said f of a does not equal f of b. So that's one of the reasons, because otherwise we have something that, it's meaningless.
Okay.
So in this, just let's wrap it up here. For this example, then n equal f of c1 equals f of c2 equals f of c3. So we have at least one. In this case, we have 3 of those. One of the application of the intermediate value theorem is to solve a polynomial of a higher order than quadratic. So here we have a cubic polynomial, f of x equals 4x cubed minus 6x squared plus 3x minus 2. We have two assignments here. First of all, we're going to use the intermediate value theorem to show that f of x has a root between x equals 1 and x equals 2. And the second part will be to approximate that root, the value of the root, to, let's say, do 2 decimal places. So, first, use intermediate value theorem, IVT, to show, this is not a proof, just to show that f of x has a root between x equals 1 and x equals 2. Part B, approximate the value of the root. To 2 decimal places. Okay, so in part A, we need to show that there is a solution to f of x equals 0 on the open interval 1 and 2, between 1 and 2. Okay? So let's write it. So we need to show that there is a solution to f of x equals 0 on the open interval 1, 2. Okay? So we need to convert this statement to the terms of IVT. So we need A, we need B. So obviously the choice will be A equals 1 and B equals 2. So let's write in terms of the intermediate value theorem, A equals 1 and B equals 2, right? And what about N? What number will be N in your opinion? Remember, IVT tells us that between A and B there is a number C such that f of C equal N, where N is the value between f of A and f of B. Spike, you want to tell us?
No, my question is, why is f of x equals 0?
That's the root. The root is the x-intercept, or the value of x when y equals 0. So what is N? What's value of f of x we are looking at? Hint, hint. That will, I'm sorry? No, you're talking about x value. We're looking at a value between 1 and 2. So 1.5 may be a good starting point. We're going to start at a certain place between 1 and 2. But what about y value? What y value we are looking at? 0, exactly. We are looking for the root. The root is the x value when y equals 0. So n equals 0. Okay? To use the intermediate value theorem, we need to show that f of 1 and f of 2 will be on either side of the 0. If one is positive, the other is negative, or the other way around, then we are good, because n is supposed to be a number between f of a, namely f of 1, and f of b, namely f of 2, right? So we need a number, we need a function value that is greater than 0 and less than 0. So let's see if this is this doable. So we say the following. This is what I'm going to write what I said. I said that if n equals 0, if n equals 0 is a number between f of 1 and f of 2, then by AVT there is a number c between 1 and 2. Then by IVT there is a number c is greater than 1 but less than 2, such that f of c equals n equals 0. Okay? So this is what we need to do in order to show that the root exists. So let's start with f of 1. Okay? What is the value of f of 1? That's easy. 4 minus 6, so minus 2, plus 3, plus 1, minus 2. So f of 1 equals negative 1. F of 2 equals what? That takes some doing. 4 times 8, 32. Minus 6 times 4, 24. So we look at plus 8, plus 6, plus 14, minus 2, plus 12, unless I screwed up. Is it plus 12? Yes, it is. So this is good. F of 1 is negative, f of 2 is positive. So we have n equals 0 is a number between, is greater than f of 1 and it's less than f of 2. And therefore, we can say there exists C in such that C is greater than 1 but less than 2. So we finish part A. We show that this function is a root. We can say so f of x equals 0 has a solution at x equals c such that this is repetition basically, such that f of c equals 0. All right. I think the last sentence was a little bit redundant. Part B, we need to actually calculate this number, right? And one suggestion earlier was in answering another question, I said, let's start with 1.5. Matter of fact, we're going to start with a number between 1 and 2, and by trial and error, we're going to pick up two numbers. Let's write. We approximate C by choosing x equal A and x equal B closer to each other. So these A and B are a little different. while maintaining that one is negative and one is positive. F of A is still negative, F of B is still positive. So we narrow. If our initial A and B was 1 and 2, now we can narrow it down while keeping F of A, the new A, still negative, F of B, the new B, still positive, and N equals 0 is still in between. Okay, so let's write. We approximate C by choosing new values x equal A and x equal B closer to each other. Okay, all of this while maintaining f of A is negative and f of B is positive. For example, and this is where you need to play with the calculator. You start using some increment, some steps. Let's say you can start with increment of 0.1 or 0.2, so 1 becomes 1.2 and 2 becomes 1.8. See, you move 1 to the right, move 2 to the left, and you check, can I find a number between 1.2 and 1.8? The answer is yes. 1.2 is still going to be negative, 1.8 will be still going to be positive. Matter of fact, and if you play with it, you can start with closer, so for the sake of time, let's choose A equals 1.2 and choose B equals 1.3. Okay, turn out that f of 1.2 is still negative, which is, if you calculate it in a calculator, it will be negative 0.28, right? So it's negative, and f of 1.3 equal positive 0.548, and you can try it on your own. So from here we get that C will be a number between 1.2 and 1.3. Okay, but this will give me one decimal point. So what I'll do next, one decimal place, I should say, I can try something closer. So now, if we are, instead of human calculator, we are machine calculator, we're going to change the increment between 0.1 to 0.01. We're going to change by hundreds instead of by tenth. Okay. For instance, we obtain a finer estimate by choosing, let's choose A equals 1.22 and B equals 1.23. So we are still very close to each other, but first we need to verify that we keep f of A negative, f of A positive. So f of 1.22 equals negative 0.007008. So it's negative. On the other hand, f of 1.23, let's see what this come up with the calculation. It's 0.056 and then 0.68. So this is positive, so we are good, and now we can choose C to be a number between 1.22 and and 1.23, and we are now accurate within 2 decimal places. Okay, so this will be our solution. So we can choose, we can cut right through the middle, or we notice that we are coming closer to 0 on the 1.22 side rather than the 1.23 side. So we can assume correctly that we're closer to 1.22, but we can't go wrong if we say 1.225 or 1.224 is the solution. Okay, at least we reached that accuracy of 2 decimal places. We have 5 minutes, so let me switch here.